various reasons, various excuses. Luckily, someone made an excuse that they'd also tweeted before and showed the evidence for, so I knew they weren't lying. It's nice to see you lasting until the final day, sort of the final part of the course, the final part of the general linear model. And I figured it could make sense to start today seeing if there's any questions from yesterday. I'll be going back over the p-value, I'll be going back over standardization, I'll be going back over some of the concepts, so I'll be talking a lot about probability distributions today as I introduce the new concepts. But is there any sort of anything you'd like me to, that I could briefly cover up again, quickly, and I can say whether it's in the notes or not, that's not too deep a philosophical issue before we get started? Anything that you feel like you missed that was a key part for understanding? Yes?
Would you mind repeat the argument for why what we discussed yesterday with the null hypothesis, why we cannot say anything about the alternative hypothesis?
Because our analysis doesn't actually pertain to the alternative hypothesis. We can't say anything, probably a better way to say it is we can't say anything directly about the alternative hypothesis. So all the probability value that we get at the end does not speak directly to the alternative hypothesis. The probability value that we get at the end when we calculate a p-value only relates logically to the null hypothesis. Because the formal statement of the p-value, the formal meaning of the p-value is the probability of getting a test statistic as big or bigger than this, given that the null hypothesis is true. So that's the probability of getting something that big conditioned on the null. So you can't formally refer to the alternative hypothesis.
So you don't get positive knowledge about the alternative hypothesis?
You get positive knowledge in the extent that you reject the null. But formally, you don't get any positive.
You get positive knowledge about the null hypothesis. You get basically you get no knowledge.
Yeah, you have to. So you have long-standing issues with Popperian epistemology and walking backwards towards truth. That's essentially what you're doing, is walking backwards towards truth. You never see the truth.
So the alternative hypothesis is just like the most likely other explanation until we have proven it.
The framework assumes that you've set up your experiment it basically assumes that you've got crucial experiments. So you've set up the framework so that there's only two competing hypotheses. One's the null hypothesis and one's the alternative hypothesis. And when you reject the null hypothesis, the only thing that's left to be true is the alternative hypothesis. But we can't know that. And there's a whole bunch of social practice that goes into doing that, and nobody actually ever does that. So that's what's called the null hypothesis significance testing, so NHST. And it's just that p-value part that's specific to that. All of the other stuff that we've talked about is more general. So when we talk about distributions, this is all very relevant for Bayesian inference as well, and for parameter estimation. When we talk about t-statistics, you use t-statistics in estimation. And you use a similar kind of formalism, basically the difference between two means, and then punish yourself by how much noise is in your data, or how little you know, or how much uncertainty you've got. That's the same way of thinking about comparing two different means, or two different samples, in Bayesian inference as well, and in parameter estimation as well. So it's just that p-value thing is tied to the null hypothesis significance testing. So when I say null hypothesis significance testing is problematic, it's only that part I'm criticising. All of the rest of the knowledge is useful for other contexts. Okay?
One more question, the effects of sample size, and is there any good golden rule of thumb as how you should go about sampling?
Yes. So you're thinking statistical power. So there is something that journal editors might want to see and that grant agencies might want to see when you're designing an experiment. And that's that you've got enough, you've got a big enough sample in order to have the information that you need in order to detect an effect if it's there. And we call that power. And the way you can think about that is in terms of what we call a confusion matrix. So you can imagine just a 2x2 matrix where you say, is the effect really there? And what do I find? And you can have 4 situations. You can have the situation where the effect is there and you do find it. And that's good. Sorry, I'll give that a tick. The effect's not there, and you don't find it. So that's a good situation, but you don't want to be in either of these situations. You don't want to find an effect that doesn't exist, or miss an effect that does exist. And we've got, in null hypothesis significance testing, we've got numbers or statistics that we use to tell us the probability that we're in this situation. And the one that we have here is the p-value. And here we say we're only going to tolerate a 50% chance of doing this. Sorry, a 5% chance of doing this. So this is 0.05. So that's where we're down here. And that gets us out of this situation, where we find an effect that's not really there. But we also have the problem of not being able to find an effect that really is there. So by chance, missing out on an effect that actually was in the data. So by chance we've sampled in such a way that it looks like from our sample that our effect wasn't present. So we give some drug to a population, so we give some drug to 30 people, and it just so happens that we pick 30 people that the drug's not particularly effective on, so it looks like the drug's not going to have any effect in the population. But actually it would if we had a sample different. We call that power. So what you want to do is increase your power, and the way to do that is to collect more subjects. Because do you remember when we're talking about the standard error of the mean? The more subjects you've got, the more likely it will be that the mean of your sample will be closer to the mean of the population. So your parameter estimate will be better. And 2 pieces of information are required to calculate this power statistic. One is how much power your study will have when you run it. So how much, when you go to run this study, how much power will you then have? One is the number of subjects, and the other is the size of the effect. Now how can you know that in advance? That's the tough part. That's where you have to look at similar studies that have been conducted before, and the rest of the literature, and stuff like that. Which isn't always easy to do, and isn't always obvious. So what people normally do is they divide the world up into small effects, moderate effects, and large effects. Small effects, you might say, is an effect size of 0.2, of 1. A moderate effect might be 0.5, and a large effect might be 0.8. So you power your study in order to find an effect of 0.2, which would be a small effect. So we believe this is going to be a small effect, so we go roughly for 0.2. I don't like this concept so much because it sneaks Bayesian ideas in. Like it's saying, what's your prior beliefs about the data? It's not really doing this null hypothesis significance testing if we don't have any prior beliefs and everything's objective. It's saying that, what are your beliefs about what's there? And you should select the number of subjects on the basis of what you believe is going to happen. If you're going to do that, you might as well use Bayesian. So that's why I took a big long pause when you asked about that, when you asked that question. And the other thing is, people also calculate power after the study and say, well, I had enough power to detect effect size I had. But you're not allowed to do that. That's not logical. And that's not legit. Okay, so that's why I don't cover powers in the slides, but now you know about it. And it's important to know about.
There's no formula you can slot in.
There's a formula you can slot in. There's an app called G-Power, and what you do is you just say what your effect size is and how many subjects you've got, and it'll spit out a power value. And you just use G-Power to calculate your expected power, and you use that for grants, basically. Not journals, because then you've already got the data, unless it's a pre-registered report. So the context that you'll use that in is in grants, mostly. And that's because people don't want to give you money unless, so people want you to justify how many subjects you're collecting. So it's a very frequentist concept that solves a Bayesian problem. Okay. So let's get into the lecture today then. So the course outline, following our schedule, is as follows. We had the first lecture, which was approaching quantitative research, where we talked about these philosophical assumptions, and we walked through R, and you learned about some data concepts and some programming concepts, and you've since used all of those data concepts and programming concepts. Lecture 2 and day 2, we talked about samples and populations, and we talked about models, very simple idea of what models are, and hypothesis testing, sort of the hypothesis testing framework, and learned about distributions, which is all valuable stuff, and tried out plotting your data and using some different functions to sort of pick out bits and pieces of data frames to make new data frames, and to test your hypotheses. You ran a t-test, and got some more practice on these data concepts and programming concepts. And in today, we'll sort of finish up this framework of what's called the general linear model, and we'll talk about correlation and regression. And most importantly, you'll see how correlation and regression is sort of the door to many, many, many other forms of statistical analysis. So this is sort of the first step that you take to a very general view of statistics in linear modelling, which is linear modelling. And in the exercises, we'll play around with this a bit, and you'll build your own linear models, which is what we finished on yesterday. We'll follow up on that. You'll learn how to interpret one of these tables, these outputs from linear modelling, and to build your own tables. And this afternoon, if there's time, we might even get to the point where we talk about nonlinear effects. What I won't cover is dependencies in data, like we talked about yesterday when we talked about paired samples t-tests. For that, you'll need mixed effects models or hierarchical linear modelling, but you can follow up on that yourself. And I won't talk about what you do when you've got a binary outcome. For there, you need something called logistic regression, but the concepts are the same. I might draw some concepts on the board for you, give you a sense of what it is, but you can look that up yourself and follow up on that. And a lot of the ideas that goes into this sort of framework can be extended also to logistic regression. And that gives you a lot of tools to analyse a lot of different sorts of data. And with all of the knowledge that you've got about distributions, you can understand also the beginning points of Bayesian analysis and parameter estimation, even though that will take more work. So today's topics, we've only really got 2 topics that we want to cover. The first one is correlation and covariance. And here I'll sort of very briefly cover again what observational data is. This should be fairly intuitive to most people here because most of you work with observational data. I don't think we had anybody that works with experiments except maybe Leah. And we'll talk about covariance, and I'll introduce a new statistic called the correlation coefficient, or R, and R squared. And then we'll talk about the general linear model. And this will be revision on the concept of a statistical model. We'll talk about bridges again, just to sort of refresh those ideas. And talk about the linear equation, which is the same linear equation that you used in high school, y equals ax plus b. We'll talk through that again. And I'll talk about how you can use that to understand what an effect is and interpret effects. And I'll show you how we can start to generalize from there to something that we call a general linear model. And then in the afternoon, we'll work with LM and do some more plotting and do some more messy data. Okay, so starting with correlation and covariance. So observational data comes from a particular type of study. There's 3 types of study. There's experiments, observations, and quasi-experimental designs. And experiments, what's an experiment? Well, when you've got an experiment, if we're going back to this language that we started with, where we're not talking about causes and effects, we're talking about dependent and independent variables. So we're analysing the event structure of the world, or the causal structure of the world, in terms of things we can manipulate and things that we can measure, and then our imagination fills in the gap. And our imagination, when we're scientists, is intersubjective theory. Then we have this clear distinction between dependent and independent variables. Everything we've manipulated is independent variable, and everything we've measured is a dependent variable. So in other words, there's a clear distinction between what's being measured and what's being manipulated. And then we can make inferences about the causal structure or the event structure of the world. And for that sort of thing, we can use t-tests, basically. Observation's different. Here, we don't have independent variables, we only have dependent variables. We're not manipulating anything, we're just watching things as they spontaneously occur. We're going out into the field, or we're taking online data, most of the kind of data that most of you work with. And here we're not talking about causation, and we're very careful to hedge our causal claims. We're only talking about correlation. So we had a clear example from the exercises yesterday. And that example was the question that we're asking, which is the number of cylinders in a car correlated with the fuel economy of the car? So if we observe the number of cylinders a car has, and we observe the fuel economy of that car, we can ask if there's a correlation. We can also run an experiment, build a new car, or build a simulated motor, and see what its fuel economy would be. There are some more examples that we didn't get to, but that will be in the notes when I share them with you for the exercises from yesterday. Is life expectancy correlated with time? So as we've gone on the last 60 years, 70 years, has people's life expectancy increased? Is there a correlation between time and life expectancy? Is life expectancy correlated with fertility? So is the number of children women have in the world, ignoring country boundaries, correlated with the life expectancy in the population? Is life expectancy correlated with fertility and the region that people come from? So are there relationships between region where you measure, so Northern Europe, Southern Europe, Oceania, North America, that sort of thing, and the number of babies that are born, and life expectancy. So there's a couple of examples there, but this is all sort of very familiar, I imagine. And so this, we talk about correlation. So this is where our word correlation comes in. Yes?
I don't understand the difference between cause and correlation. Could you just talk about
We can make causal claims within this framework if we've done an intervention, basically.
Okay.
And so if you're interested in this topic, there's a philosopher named Peter Woodward who's essentially written a philosophical theory of how we should understand causation ontologically, called Making Things Happen, which uses the general linear model. He's worked in econometrics and philosophy, which uses the general linear model to provide a theory of causality. And he says that any time we've got an intervention, we can talk about causation. And it gets weird because he's a philosopher and he talks about, well, any time God could have done an intervention. Yeah. So anytime objectively there could have been an intervention, then we can talk about causality. So read that book if you're interested. It's very big and very complicated. So if we're not intervening, then we can't talk about causation. But you'll see these two things will dovetail again at the end of the lecture. So causation doesn't exist in our statistics. That's the point. Causation exists in what we do in the world, around our statistics and around our models. So let's take this question. Is life expectancy correlated with fertility? And there's a number of different ways we can pose this question. And they all have the same meaning, but the different ways of posing them opens up different statistical concepts for us. So we can say, instead of saying, is life expectancy correlated with fertility, we can say, is a change in life expectancy related to a change in fertility? Or vice versa. because we don't really worry about the direction of the effect here. So is an increase in the fertility of the world somehow related to an increase in the life expectancy of the people in the world? Another way of saying this is by using this word association. So is life expectancy associated with fertility? So now we're talking about an association, we're talking about a relationship. Now that we've got focus on this word association, we can ask whether or not this association is reliable. Is there a reliable association between life expectancy and fertility? Another way of saying this, because we're talking in terms of change, is variation. So we can say, do life expectancy and fertility vary together or co-vary? Such that if one varies, then the other one will vary with it. So do they co-vary? So this is the term that we're going to focus on, this covariance. And all that means is change in one. Is change in one associated with change in the other? And this is a statistical concept that we can now build up given the tools that we've already got. We just need one term from yesterday, and that term is variance. So I was asked yesterday, when would you ever use variance and not standard deviation? Remember, variance is the last thing we do before we get to standard deviation, and the answer is now. So variance comes in the second last step when we're calculating standard deviation. And so a refresher from yesterday, so that you can remember what standard deviation is, so that you can remember what variance is before going on. I'll just show you the same slides from yesterday. Remember that standard deviation just means the standard, or the average, the standard distance, or deviation of each score from the mean. So if we have this sample of 5 scores of our cortisol study, and we have our mean here, then what we're interested in is the average distance of each data point over the line. So we do that by adding up all of the distances and dividing by the number of subjects. And that gives us the average distance. But we get this problem of the sign flipping all the time. So we need to cancel out the sign. So the way that we do that is we square. So we have the squared difference. We square the difference between the scores and the mean. We do this because squaring makes everything the same sign. So this gives us the squares of the summed difference. Is this okay? Is this familiar? Yeah. So this we also call the sum of squared errors. It's a term that comes up when you're sort of working within an ANOVA framework and within a linear modelling framework, or it gives us the variance if you divide it by the number of subjects. Okay? And then if we want, we take the square root of that to get the standard deviation, to put everything back in the same units that we started with. And we saw that the equation was this one. And we did a worked example. Okay, so let's look at this equation again. Here's our equation for standard deviation. What are we going to do with it? Well, this is our population standard deviation. We need our sample standard deviation. How is this different from the equation for our sample standard deviation? Well, we have to correct for the fact that we're already making a guess. So we have one less degree of freedom. So instead of having n, we're dividing this sum by n, we divide it by n minus 1 to punish ourselves, to give ourselves less certainty. So this is our sample standard deviation. So how do we get our sample variance then? What would our equation for sample variance be? Any takers? What do I change about this equation to make it our equation for sample variance? Yep.
You do not square it, so you
Remove the square root. So that's it. That's our sample variance. So what we're doing here is we're subtracting the average of the sample from the score, squaring it to get rid of the sign, doing that for each score and adding them all up, and then dividing by the number of subjects minus 1 to punish ourselves. That's it. We can write this another way. We can, instead of writing this as the brackets squared, we can get rid of the squared symbol. So here we have 2 squared. 2 squared really means 2 times 2. Right, so you can write 2 squared like this, or you can write 2 squared like this. So let's do that. So here you have to imagine that there's a times sign in the middle. There's a ganger. And that's the same equation, that's still our sample variance. So this is our sample variance. Okay?
Why is it written different? This is
Because we're going to use this format in a second. So I just want you to keep this in mind for now, and we'll come back to it. So we're getting rid of that squaring because we're going to change one of these. And you'll see which one will change. And you can see that by coming back to our question. So our question was, is life expectancy correlated with fertility? And we've formulated that in all of these ways before, so that's familiar. And what we're really asking is, do life expectancy and fertility covary? Does change in fertility, is that associated with, reliably associated with change in life expectancy? That's what we're interested in. So, sort of a more general way of saying that, does change along the x-axis, is that associated reliably with change along the y-axis? That's what we're interested in when we're talking about covariance. Okay? So when we're talking about change, change is variance, right? Change is variability. So another way of saying that is to say, is variability or variance in x associated with variance or variability in y? Is that okay? So that's a graphical way to think about questions that we just asked. And since we've got a graphical way to think about it, we can translate it into a mathematical way to think about it. Okay? So here's our sample variance equation from before. This is where we ended on the previous slide. So that's sample variance. What we're interested in though is the relationship variance in x and variance in y. So how can we represent that? Well, all we have to do is change out one of the x's with one of the y's, and that gives us the sample covariance. Okay? So let's look at an example. So we've got fertility and life expectancy. And these numbers are wrong because I changed the example and forgot to change the scales. So ignore the numerical bit down the bottom. I discovered this last night and I was too tired to fix it. So we've got our figure again. We've got fertility and life expectancy. And imagine that we've gone out and measured 5 countries for fertility and life expectancy. This could be any 5 countries, it doesn't really matter. And now we've got 2 averages, right? Not just one. We've got an average from the perspective of life expectancy, and we've got an average from the perspective of fertility. So across these 5 countries that we've measured, we're interested both simultaneously in average fertility and average life expectancy. So let's put those up there. So we've got an average life expectancy, which is a mean of 70, let's say, an average fertility, which is a mean of, say, 2.6 kids per family. And these numbers are right, it's the next bit of the job. Okay, so let's keep this in mind. We've got these averages, and this is just the same sort of plot that we had before in 1 dimension. Now it's just in 2 dimensions. So let's put this over here, and let's work out the numbers. And this is where it's wrong. All we have to do is plug in these distances for y, and these distances for x, and divide by the 5 minus 1. Add them all together. So each data point, we have the data point minus the average on one axis, times the data point minus the average on the other axis. Then we go to the next data point, and and say the data point minus the average here times the data point minus the average here. Do the same thing for the next data point, then the next data point, then the next data point. Add all of that together and divide by the number of subjects. And that'll give us the covariance. And the numbers are wrong, so I just took the answer out. Okay? Any questions? Okay.
Oh, sorry.
Yeah.
What was the difference between correlation and
Covariance is we're building towards the concept of correlation. So you could say the correlation is, verbally, the correlation is the relationship between things. Covariance is a statistic that tells us about the relationship between the variables. And the correlation coefficient is another statistic that tells us about how good that relationship is. And that's what we're getting to. So we've got a problem here again, and it's a familiar problem. It's a problem that we've seen before. And that is the problem of scales. So it makes it slightly different to say something general here, because this is in years, and this is in number of births. And these are radically different scales. So one goes up to 120 potentially, and the other one goes up to, well, hopefully not too high. However many kids a family can have. But it's definitely not 120. So why is this a problem? That's an old version. We want to talk about the relationship between life expectancy generally and fertility generally. But here we have to talk about it in terms of our scales. And for this example, it's not too bad, but you can imagine you might be working with other examples. So here the scales make sense, and you might want to keep it in terms of your scales. But there might be other examples, like let's say if you wanted to look at the relationship between the attractiveness of somebody's Facebook profile and how long people view the stimulus. If you measure it in seconds, or if you measure it in milliseconds, the time of your viewing, or if you measure attractiveness on a scale from 1 to 10 or on a scale from 1 to 5, you'll end up with different covariance scores, and you won't have anything general to say. So anytime you get any flexibility in your scales, you lose the ability to say something general. So for many cases, we need to fix this. Because if we change the scales, we change the covariance. So if we were to calculate age, sort of life expectancy in months, which you wouldn't necessarily do because we've got a stronger convention here, you'd have a different covariance score. So what we want to do is have a standardized scale that gets the units out of there. We want to get rid of units. We want to have no units. We want to have be able to look at the relationship in terms of more general units. And we did that yesterday. We did that by standardizing the scales. So yesterday we went through this when we talked about the Z-score. So remember what the Z-score does? The Z-score transforms your scale so that it's no longer in the units of whatever it's in. It transforms it so that now it's in units of standard deviations. So if we calculate Z-scores for our data points, when we're calculating the covariance, then that gives us these scale-free values that we're interested in. Because now we're not talking about, say, attractiveness on whatever rating scale we used, or age in years or months. Now we're talking about age in standard deviations from the mean. So if Japan has a very high life expectancy, we can express this as Japan is 1 standard deviation higher than the average, or 2 standard deviations higher than the average. And that allows us to speak more generally. And it also allows us to do what we want to do, which is calculate the correlation coefficient. And remember that we do this by centering. So subtracting the average, the scores from the average, and then dividing by the standard deviation of of all of the scores. And it's that dividing by the standard deviation that changes the units. So if you divide by something, you generally change the units. So if you've got seconds and you divide by 1,000, you get milliseconds. Here we're dividing by standard deviation. That gives us units of standard deviations. Okay. So we divide by S. That's the important thing here that we used yesterday when we were talking about z-scores for standardizing. So whenever you're standardizing, you're forcing it to be in a standard normal distribution with a mean of 0 and a standard deviation where one standard deviation is equal to 34% of the area under the curve. So that's what we're going to do here. We've got our covariance. We've calculated that in terms of the scales that we've been used to measure the thing that we're interested in. And we just divide that by the standard deviation of each of the data points for the scales that we're using. So we divide by the standard deviation for fertility and the standard deviation for life expectancy. Okay, so we have the covariance divided by the standard deviation of both variables, both dimensions. And that we call R. And that's the correlation coefficient. Okay? So this is Pearson's R, or the correlation coefficient. So what does R mean? You may have seen R, you may have heard R, you may have heard of correlation coefficients if you've read empirical literature. Might be something that you've sort of glanced at and come across. How do we interpret this?
John,
Yeah.
Can you use the covariance for anything, or is it like you measure the variance to get the standard deviation?
It's kind of like the variance, where now the variance was useful to get the covariance, and then we got the R value. The covariance can be useful in other equations.
But not just as a
Yeah, because the
number that we can
no,
report on. It's not.
no, generally no. But just what the covariance is the unstandardized R value.
Okay.
So if you want to keep everything in the same units that you've measured in, then you can report the covariance, and that might be useful in many different situations. Or if you've got some other statistic that you want to calculate, you can report the covariance for that, or you can use the covariance in that. But really, the correlation coefficient is just the standardized covariance. And covariance is just a statistic that tells us the association between change in one thing and change in another. And it does that using the same equation that you use for standard deviation. And that works because standard deviation tells us the average distance from the mean, whereas covariance tells us the average distance from two means simultaneously. That's the trick. Okay, so we get a score out of this, and it's from 0 to 1. What does it mean to get a score of 0? What does it mean to get a score of 1? What does it mean to get a score of 0.5? What does it mean to get a score of 0.7? So when R equals 1, sorry, it's not from 0 to 1, it's from -1 to 1. What does it mean to get a R of -1? What does it mean to get an R of +1? What does it mean to get an R of -0.5? What does it mean to get an R of -0.2? What does it mean to get different values? When your correlation coefficient's negative, when you've got an R of, say, of -1, anywhere between -1 and 0, then you've got a negative correlation. What's a negative correlation mean? It means that as x goes up, y goes down. So less viewing time for more attractive profiles, for this example, or less fertility for higher life expectancy. If your correlation's exactly 0, then there's no correlation. There's no relationship between the variables. If your correlation's positive, it means that there's a positive association. It doesn't mean good positive association, it just means that as x increases, y increases. So as fertility increases, life expectancy increases. So that's the sign of the number. What else is there? What other information is there? There's also the sort of the value of the number, or how high the number is. If you have an R equal to 0, then you've got no correlation, then there's no pattern in your data, you stop there. Or if your correlation is not significantly different to 0. If your correlation is between 0 and 3, 0.3 roughly, this is kind of the rule of thumb norm. There's no logical reason for choosing this. This is just in the kinds of fields we work in. If we get a correlation up to 0.3, we say it's a weak correlation. And if it's sort of above 0.8, we say it's a strong correlation. And if it's in the middle, sort of between 0.3 and 0.8, we say it's a moderate correlation. And that's going to be field dependent. But what you notice here is, and what sort of matters here, and what this captures, is that if we were to sort of draw a line through the data that describe the trend, and we'll talk more about this line later as we go on, the higher the correlation, the more the data points would cluster around a line, the more the data points would draw a line. So if you have a perfect correlation of 1, then what you'll get is data points drawing a line through the space, which means that every time you get an increase in X, you systematically know you're going to get an increase in Y. And then they'll be perfectly correlated. Importantly, this value doesn't tell you anything about the slope of this line, the angle of this line. So it doesn't tell you how much Y is going to increase as a function of X. It doesn't tell you how much changing X will lead to or be associated with the change in Y. All it tells you is this clustering of the data points in a line through this space. So that can be illustrated like this. All of these correlation coefficients are 1 and minus 1. But the line's sort of slopes differ. So you could have a flat line that's got a high correlation. Well, this is going to be 0. But as soon as you start to get some sort of slope in there, you've immediately got a correlation of 1, if all of the dots line up perfectly. So how cloudy is the data? Think of your data as a cloud through two-dimensional space. So, how do we interpret this? Well, remember, a correlation can be thought of kind of like an effect. So it's kind of like the difference between two means, in the sense that the same way that two means can be different due to chance, without actually being different, as we saw yesterday. So when we talked about the null hypothesis, we can have the null hypothesis being rejected even though that we shouldn't have. And that's what the p-value is supposed to tell us. What's the probability of that happening? Two variables can be correlated or look correlated due to chance without really being correlated. So we want to know if our correlation is significant, the same way we wanted to know whether the difference between our two values was significant. Okay, so how do we tell if our correlation is significant? We do exactly what we did yesterday. We run a t-test and we get a p-value. So when you do a correlation in R, what you're doing is you're asking how cloudy are my data? How big is the cloud? How diffuse are my data? Are they in a straight line altogether or are they diffuse? And if they are in a straight line, which directions are going? Can't say anything about the slope. And is that structure accidental or not? And so if we want to ask if it's accidental or not within the null hypothesis significance testing framework, then what we need to do is, same procedure as yesterday, run a t-test and calculate a p-value. So if you remember from yesterday, we had our t-statistic, which looked like this, and that was the mean of the sample of minus the mean that we're interested in, or the number that we're interested in, which was this 23 micrograms per deciliter, this cutoff point, divided by the standard error, which is our punishment. And I said that this is a very general formula, sort of a general format of formula, called a test statistic. And we saw that this can vary, so this is different if you're looking at the difference between two groups that have got a consistent relationship, where you're testing the same entities twice, versus if you've got two means that you're looking at from two samples, rather than just a mean and a single value. But what's consistent here is that you've got an effect, which in this case is difference between a sample and say a consistent value, divided by an estimation of how well you think you've done in getting that mean, in how well you think your sample mean reflects or maps onto the real population mean that you don't have access to. So your punishment of yourself for the quality of your sample. And then what did we do next? We took the p-value, the t-value, and we plotted it on this t-distribution. T-distribution looks like a normal distribution. It has all the same properties of distributions. It has parameters. It's a probability distribution, so the area under the curve is equal to 1. Similar to normal curve. And that allows us to then take our t-value that we got, put it on the curve somewhere, calculate the area under the curve, and that gives us the probability of finding that t-value or anything more extreme, given that the null hypothesis is true. And that's our p-value. We saw that this is a general form of a test statistic, the effect that we're measuring over our error related to sampling. So what we want now is a test statistic that's appropriate for the correlation coefficient. And I won't go into too much detail, but this is it, if you need it. That's for your reference. So this is how you calculate a t-value for a correlation coefficient. And once you've got a t-value, you can calculate a p-value. So when you run a correlation, you get a correlation coefficient, which is R, which is your standardized covariance, which tells you how much change in one variable relates to or is associated with change in another variable on a standardized scale. And that tells you the strength of or the direction of your association and the strength, but not the slope. You get a t-value for that you can then plot on the t-distribution. That'll give you a p-value, which will tell you whether or not that correlation is significant, that r-value is significant for the sample that you've got. Is that okay? Any questions? Okay, good.
What's the difference between strong, if it's strong, it can be a strong correlation by accident, is it?
Yeah, and there'll be, and the p-value tells you the probability of that happening by accident.
Okay.
So the p-value tells you, yeah, exactly. So the p-value will tell you the probability of getting a correlation coefficient, open from there, of a correlation coefficient that's significantly different to 0, given that the null hypothesis is true. Where the null hypothesis in this situation is that there's no relationship between the variables. Okay? So we still need to do some interpretive work. We're not quite done interpreting. All of this interpretation so far has been related to statistics. There's also interpretation that goes on outside of statistics. What does it mean when we find a correlation? Well, correlation doesn't imply causation. This is something that we statisticians beat scientists over the head with all of the time. Why doesn't it imply causation? 3 main reasons. One is intervening variables. So you might have something that's causing both. So, for instance, a good example is red wine and life expectancy. Always gets put in the news as drinking red wine increases your life expectancy. It could be that if you have more money and you're more upper class, you're more likely to be drinking red wine instead of beer in whatever culture this is being measured in. So it could be the class difference and economic differences, socioeconomic differences are causing both consumption of red wine and increased life expectancy. Similarly for fertility, there might be some intervening variable between life expectancy and fertility. It's not the having of more children that would necessarily, it might not be the having of more children that necessarily could cause a positive correlation with life expectancy, or the having of fewer children that could cause a negative correlation with life expectancy. So not just because a society has fewer kids do people live longer. There might be something causing both. There's a direction of causation issue. So if you're just looking at the world and not intervening on it, you don't know which thing's causing what, even if you don't have intervening variables. So imagine that there's no relationship, that there's no intervening variables, and we know that for a fact, between life expectancy and fertility. And imagine that we find that there's some positive correlation between fertility and life expectancy. We don't know how to interpret that. We don't know how to interpret whether or not increasing life expectancy is causing people to then have more children, or the joy of having children around is making people live longer. We don't know which one. There's also coincidence. A great example here is there's been an increased incidence of pirates on the seas recently. And we've seen simultaneously with that an increase in life expectancy. So if we were to calculate the number of pirates on the seas and life expectancy, we might see a positive correlation. But does that mean that we should then go and invest in having more pirates to increase our life expectancy? No, this is just pure coincidence. So be careful with correlation. Okay, so that's correlation and covariance, and we've come quite far quite quickly. So that means that you've learned stuff yesterday that you're using today. If you want, I think it could make sense if we take a break before we move on to the next part, which is the general linear model.